Okay, so welcome to lecture 19. The topic of today's lecture will be actually new thing in coding theory called locally decodable codes. So, without much ado, we already saw a flavor of this last time when we were talking about read Muller codes decoding. We had that they showed that they had a local decoding feature in it. We will sort of more explicitly spell it out what locally decodable codes are. So decodable code. So what's a locally decodable code? You want to it's sort of the intermediate mix between on one. You want to be able to locally decode the message. You want to be able to decode the message from possible corrupted versions of the code word, but you don't want to read the entire code word to read the message. Suppose you want to read only the 10th bit of the message, then you want to read just few locations in the received word and be able to do it. And we will there will be two parameters of interest here. L, which is some positive integer. This will be the locality, how many queries you are going to make. And epsilon is the fraction of, epsilon is going to represent the fraction of errors that we will be able to. So we will say that a code C from sigma k to sigma n is Q. L epsilon locally decodable. Or in short, L epsilon LDC, if the following, if there exists a decoder, it will necessarily have to be a randomized decoder. The decoder doesn't get explicit access to the entire received word. It only gets oracle access to the received word, such that on input y. Now, why we're going to view it because it's oracle access. I'm going to view it as a function from n to sigma. For every code word bit, code word location, it tells you the one, but you get only oracle access. Oracle access with promise that there exists m and sigma to the k such that delta y with C of m is less than epsilon n. So you promise that there are not too many errors. Then you're also given an explicit input, an I and k. You're asked to, this is an explicit input. So D probes y or queries y. At most L locations and outputs some in sigma, and we should have this property that for all I in k, for every one probability that dy is equal to mi should be greater than 2/3. Yeah. So the epsilon will be smaller than, we'll only consider much smaller than the half unique. In particular, this would force it to be epsilon to be within the half. The definition doesn't suggest it, but because we want this, that's the only way you can have it. Okay, so that's going to be the definition of the loaded definition. Quite a word mouthful, but it should be clear what it means. The key is this one we want. Okay. So why do we require such sort of locally decodable codes? It's sort of, suppose you have a library and you want to encode a digital library, you want to encode the library. One way, and you want to be able to withstand, say, errors like 100th corruption. So one way to do is encode the entire library. Say you have the ACM library, encode the entire, or the TIFR library, encode the entire TIFR digital library as one using one nice code. Certainly it can withstand 1/10 corruptions. But now, if say you want to, I want to read the 14th book or some particular book in the library, the only way I know how to do it is I have to decode the entire library, the encoded version of the library, to pick up the book. You don't want to spend so much time. Each time I want to read a particular book in the library, you don't want to do it. You want to be able to get, if I want to read only one part of the original message, I should not have to decode the entire code word. I should be able to decode. So you want to be able to decode just a small part of the code word because you want to only read a small part of this one. Now, the other option is you take each book and encode it and keep it. So that now you certainly in locality you get it. You want to read the book, very good. But the point is, if you're going to withstand 1/10 of the corruption, you can just go and erase 1/10 of the encodings of the books. If the book you're completely messing it up, there's no way in hell you are going to be able to recover the book from this one. So you still want to be able to withstand 1/10 of errors globally. So with respect to a particular book, this 1/10 of errors could be enough information to kill the whole content of the book, but yet you want to be able to recover. So the setting is extremely well motivated. Question is, do there exist such locally decodable? So is the question clear? And we already saw some examples of this. Read-Muller codes are great locally decodable codes. So let's actually sort of go and recall what Read-Muller codes get you. So the definition and all clear of locally decodable codes. So our main goal today will be trying to understand how small can this locality be. The locality N is the locality of the locally decodable code. Of course, if N is N, then that's trivial. We are basically reading the entire code. I want to make L as small as possible, and we try to make L to be something like a constant. That's going to be the goal. I want to tell you, so the question we want to ask is, are L epsilon LDCs, rather do L epsilon LDCs exist? Or constant L. So we ask two questions, both they want whether they exist, and then we will want explicit codes also in this here. So I want to say, if you just care for constant here, in fact, they do exist. The best constant, what's the best constant you can hope for? L. 2 is the best constant one can hope for, and they do exist. We already are very comfortable with certain LDCs which are 2-query LDCs. So I want to say, if you look at the Adamath code, which maps 0,1k to 0,1,2 to the k. It's an exponential. This one basically it's going to map x to the function which takes y to inner product x. That's so it's a 2-k long string, and the string I'm doing it as a function. This is what the Hadamard encoding is. So we saw that. So suppose we want to encode the ith. We already saw this. Suppose we want to encode the ith bit, decode the ith bit of the Hadamard coding. So suppose I promise you that f is some function from 0, 1 to the n, sorry, 0, 1 to the k to 0, 1. Suppose I give you the promise that f is some function such that delta f of the Hadamard encoding of
It's 0 1 for 2.
huh?
It is from 0 1 for 2.
No, f is from 0, 1 k to 0, 1. F is a valid, it's a received word, so I'm just, it's a 2 k long string, but I'm doing it as a function. Whether there exists x, say this is less than say 1, 2 k by some delta into 2 k. It's a small fraction. How would you recover? So I want to recover the ith bit of the message. What is one way of doing it? Yeah, so this is what we saw already. So it is, we already saw that xi is in fact the majority of, rather, this is easy to see, the probability over a random for all I over a random choice of r, f of r XOR ei minus fr is equal to xi. What is this probability? This probability is at least there's a union mode, there's a delta over here. It could be delta over here. There are 2 delta, so this is at least correct with probability 1 minus 2. So the Hadamard code is extremely locally decodable. You can do it with as good as it, but it has a big disadvantage. And what is the disadvantage? The rate is inverse exponential. It's as bad as it. It's not as bad as it gets. Later on, we'll talk about those codes which are even worse. We'll talk about something called the long code, whose rate is inverse double exponential. So it's called the long code because it's the longest of all possible code. Okay? Anyway, so this is, it's pretty bad. By coding theory reform, you would like to get constant rate code, or at least inverse polynomial rate code. So it's a pretty bad code. So all I'm saying at the point of this is the Hadamard code is 2. And because of this 1/4, I can make it this, so I can take delta to be any number. So as long as this is greater than, delta can remain any number smaller than 1/4. As long as delta is any number smaller than 1/4, this is the advantage better than half. So think, I want to say, I can put 2 epsilon LDC for any epsilon which is strictly smaller than. So that's the takeaway from this one, but it's very bad rate. The other extreme, we looked at Reed-Muller codes, RMQ. Reed-Muller codes. So what is this one? So once again, setting it, the dimension, the number of variables, I'm working with number of variables being m, the degree being r, the field size q, the field size. So let's set it to be, the field size to be at least, it should be greater than r into 1 minus 2 epsilon. So we are in sort of the large field setting. The field is larger than. So what did we, what was the thing we saw? That is, if you want to decode at a particular point, you just pass a random affine space to that point, an affine space of large enough value, so that you do get it. A large enough dimension so that you're able to recover. Now, this setting of Q and R is to ensure that the affine space is actually, you can exactly choose just a line. It's ensured. This is just a set that you just pick a line through this point, and that's enough. And now read off all the points along this affine line. So you have a univariate polynomial. Essentially, you have this. So you have this object. The Reed-Muller code looks like this. And I want to decode over here. So I just pass a random, pick a random line. Line L. So for any Z, input is Z in FQ to the M. Pick a random line. You see. Query F on all points on line. Perform univariate interpolation. And output value. So this is one. So notice the, so I'm not going to mention the, it's a QLDC. The locality is Q, which is the size of the field. The QLDC. I'm not mentioning epsilon, you can check it, it's a constant fraction, you can set parameters that epsilon, it's in fact you can set it up such that this is exactly, it's a Q epsilon LBC. And the only reason for Q epsilon is basically because the field is larger than R times 1 minus 2 epsilon. What is the probability that a random point is erroneous? It's epsilon, that's what's given to you. So the point is now we are reading Q points. What's the probability that any one of the Q points is erroneous? Epsilon Q. So as long as the code can support epsilon Q errors, and that's got by choosing R to be small enough. The degree of the thing is small enough compared to Q. Therefore, epsilon Q errors you can withstand, and you hence are able to do this. So you can actually, this is a Q epsilon LDC. Question is how good is its rate and stuff. So let's look at the parameters. Let's flesh out the parameters a little more to find out how good its rate and other things are. So what is n here? N is Q power n. The same type of one. What is K? K is, this is the large field setting, including field. So the K is exactly m plus R choose m. This is at least R by m, the whole power m. And for our setting of parameters, R itself is, so we call that R was chosen to be 1 minus 2 epsilon times Q. R was chosen this way. Therefore, this is basically 1. That is exactly equal to 1 minus 2 epsilon by m, the whole power m. There's a Q power m that goes out, that's n. So this is the rate of the code. So depending on how I'm going to choose epsilon, this can be a nice number, a bad number, or whatever. And the locality is always, locality is Q, which is always locality which we have, locality L is by definition Q, and this is roughly like n to the power 1 over n, exactly n to the power 1 over n. So it's a very, so the point is the larger you choose m to be, it's really, really low. So ideally, I would like to choose m to be something like, how large would I like m to be? I would like m to be something like order log n. If I make it order log n, then this becomes a constant. So m to be something like log n over 100 or something, I choose it to be, then this becomes a constant. So we would, the larger n is going to be the large. So the point is, you're doing read mirror codes, the larger the ambient dimension, the more local it is. That's basically because you are just reading one line of the entire space. So what's the fraction of one line compared to the whole this one? So obviously, so let's look at the two various extreme settings. So one setting is when m is, you set m to be 1 over epsilon. then in this case, you can choose k by n to be basically k by n. So that will be n is 1 over epsilon. If it's epsilon into 1 minus 2 epsilon, basically that 1 minus 2 epsilon doesn't matter. It's just epsilon to the power 1 over epsilon. It's essentially this in this setting. So you choose that I want to withstand against epsilon errors, then you choose m to be this one, and the rate is going down. Notice the rate is going down dramatically. So you want to be withstand against epsilon errors. That means the rate also has to go down as small as possible. It's still a constant, but it's still going down with epsilon. The other extreme is I want to choose m to be log n. Log n is not doable. So in fact, you can make it log n by log n. And here what was Q? Q is, sorry, the locality. Locality is what? Locality is n to the power epsilon. So it's not yet a constant. It's a significantly small fraction of the input. It's n to the epsilon, but it's not a constant. Now I can make m even larger, not 1 over epsilon. I put it to be log n over log n. You can plug in the parameters and realize that for this setting, n will be poly k, so you get inverse exponential rate. And L, n will be poly k. And L can be made as small as poly log n. Then you just plug this and you can check that. So the larger you're making m, you're going to make L to be smaller and smaller. And here L is polynomially smaller. Here L becomes polylogarithmically smaller, but the rate has grown from has increased from a constant to has decreased from a constant to become inverse polynomial. You can go the extreme other this one. You can choose cases. This is very close to the Hadamard setting. Go all the way when Q is order 1. That is Q is roughly exactly R into 1 minus 2 epsilon. This one. In this case, what you can check the above parameters is n will actually be the L now will be Q, which is order 1. But here you have to go to constant size fields in order to get constant locality. Here you notice, you can check the above calculations, it will become k into 1 by q minus 2. So this is, so all I want to say is here is rate is constant. Let me just comment over this. So these are sort of 3 regimes. The first regime is the case in which the rate is not, it's a constant rate. It's epsilon not, no? But the locality is not very small. It's much smaller. Inverse polynomial is n to the epsilon, but not constant. Next is I've gone to rates which are inverse polynomial now, n is poly k. The locality is considerably decreased, it becomes poly log n. And the third case is in which the rate is now inverse exponential. This is like the Hadamard setting, where I have managed to get constant rates. So for a long while, it was believed that it is always the case. First, people asked, can we improve on 2 queries? Can we do anything better than Hadamard? And then there was a result in 2004 due to DeWolf and Kerenidis. 2004, it says that any 2 query LDC must have inverse exponential rate. Negative. It basically said Hadamard is the, if you care for 2 queries, Hadamard is the more or less the best that you can do. You can't do anything better. So now people ask, what about 3 and more? Can I do better? And all that we knew were these various settings of Reed-Muller code. Reed-Muller code in the various settings. That is, choose larger and larger dimensions. You choose larger dimensions, locality becomes smaller, but you pay for it in Reed. This was the setting for it. In fact, the initial belief for a long while was the fact that this was believed in the till about 2008 or 2009 with the following work. that if the locality is anything less than n, then the rate is less than a constant, and in fact is little over 1. That is the rate. Notice that if I want the locality to keep improving, that even in constant rate, the rate is getting smaller and smaller and smaller. That's one thing that happened, and said that if the locality is constant, they felt that the kernel is stable. Then the rate must be inverse exponential. This was what was conjectured, that this has to be true. Anything locality is anything better than n, then the rate has to be cannot be constant, it has to go less than 0. And if the locality is all the way to constant, this is big O and small, this is big O1. Then the rate actually is inverse exponential.
Can you explain one more on the first one?
The first belief?
Yeah.
No. It was felt that, notice all of these things, none of these things, even if I want to get some locality, some n to the epsilon, notice that the rate is epsilon to the 1 over epsilon. That's a number going to 0. That's a number going to 0. So it was felt that if you want any significant rate, you have any significant locality, you have to have rates which are approaching 0. Not rates which are not constant. Ideally, I would like to have rates approaching 1. The code is really, I'd like to have constant rate, and even better, I would like to have rates approaching 1. That is basically there's no redundancy in the code. But these constructions seem to suggest that even to get inverse polynomial locality, I need to have rates which are going to 0. So it was for a while conjectured, believed that this was the case, that any non-trivial locality would imply rates which are going to 0. So let me actually hear that. This one, all I want to say is the following. Non-trivial locality implies rate is going to 0. And furthermore, if you want the locality to go all the way down to order 1, the rate is inverse exponential. It goes as bad as possible. And both of these beliefs seem to be unjustified. We later on, around 2009, 2013, about 10 years, a decade, a little more than a decade ago, we actually came up with code constructions which refuted both these conjectures. And we will see both of these in the rest of the course. The first one, so both beliefs were refuted. The first is via something called multiplicity codes. That is, you could get non-trivial locality with rate approaching 1, in fact. It will be just non-trivial locality. It won't be locality, constant locality. It will be some polylogarithmic locality or something. But so it will give you something like polylog n locality. And rate very close to 1 as possible. And 2. So in that sense, multiplicity codes were introduced. We won't do multiplicity codes today, but a fair amount we'll spend 3 lectures, not next week, but the week after, on multiplicity. That will be the finale of the course. We'll take multiplicity codes and discuss various properties of multiplicity codes. And the other one is code based on, these were Yakanen's codes. So he showed that there are 3 query codes with sub-exponential rate. 3 query LDCs. Inverse with sub-exponential blow up, which is what means sub-exponential. So it's not all the way, it's not inverse polynomial also, but it does give you some inverse sub-exponential. So and this is low. So now that Now that inverse sub-exponential rate is possible, people possibly believe can go all the way down to inverse polynomial, but we haven't been able. So what we will see today is we will see Yakanan's construction. That's going to be the focus for the rest of the lecture. We'll take Yakanan's construction, we'll construct a constant query. The constant can be 3 also, and which will have sub-exponential rate. So in fact, so Yakanan gave this. So we won't exactly look at Yakanan's construction. Yakanan did this in 2007, and he did it. He didn't give an unconditional construction. He gave a construction assuming infinitely many Mersenne primes exist. So he used Mersenne primes in his construction, and he needed larger and larger Mersenne primes. Mersenne primes are primes number 2 power n minus 1. So he needed this. So this is it's an unproven conjecture in number theory. We don't know that they exist infinitely Mersenne primes. But subsequently, after this, rather immediately, Prasad Raghavendra gave he didn't remove the assumption, but he gave an alternate description of Yakanan's construction. Yakanan. But then 2 years later, Efremenko, in 2009, gave an unconditional construction. Using matching vectors. We'll describe what matching vectors are. So today in class, we will see Efremenko's construction, but we won't see Efremenko's, the description won't be Efremenko's original description, but we will see Madhu's and Parikshit Gopalan's description of Efremenko's construction. Because the reason I prefer this description is very much like read mother codes. That's will be what we'll be doing today. The one thing which I should have mentioned. So what I defined in lecture was only locally decodable codes. Read mother codes are a little more than locally decodable codes. You can not only decode. So if you want to decode, I wanted to say you want to decode the message. So I didn't tell you. You can tell me what the message is for read mother codes. You could always assume a systematic coding, encoding, and therefore, if you recover a certain part of the code word itself, that's what we call the message. But read mother code, in fact, says you can recover every code word bit, not just any message bit. That's what we saw last time. So these are even stronger than locally decodable code. These are called locally correctable code. So you're correcting the code word. You're not just recovering the message bit, you're actually recovering the code word bits also. These are two different things, locally decodable code, locally correctable code. Any linear code which is locally correctable is obviously locally decodable also, if you choose the right systematic encoding. So read mother codes are locally correctable. In fact, Hadamard codes are also locally correctable. The codes which we see going to construct now will only be locally decodable. I do not know how to make them locally correctable. So I'll be able to recover the message bits. I'll give you a particular encoding. It will be a linear code. I'll give you a particular encoding. I'll be able to recover the message bits, but I don't know per se how to recover the other code word bits. To recover a code word bit, I might need to. It won't be local anymore. I can recover. Of course, I can recover because I have this one, but it won't be a local procedure. Okay. Anyway, what do we want of such a this one? We want the following property. That is, I want to recover some, say, message MI. I want to say these L locations in the code. If I read these, I can get the message MI. So it's just like in Hadamard, you realize that to recover XI, you have to read F of R and F of R plus EI, both of them were. But the nice property of F of R and F of R plus EI is, though those both points were correlated random things, individually the marginal distribution on each one of them was the uniform distribution because of the choice of randomness R. And hence, you could individually assume that the error in F of R is epsilon, F of R plus epsilon is, F of R plus EI is also epsilon. Therefore, that's why you got the total error of 2 delta. The same thing will go here. What we will now try to do is, we will try to come up with a code such that every message bit is a function of some L bits in this one. These L bits will be random. It will be a random set of correlated L bits. But each of these L bits, when you look at the marginal distribution, it will be uniform. It will be completely uniform. And it will, so that each of them, so as long as each of them will be uniform, of course, they are correlated among them. So we'll just apply the union bound and show up to the union bound, you will be able to. So that's going to be our code. So we want to somehow write the message bit as some small linear combination of the code word bits. And you want several, but it's obviously you can always write it as a small linear combination. But you want to write several such small linear combinations, because you notice if you looked at right here. So notice we had that xi was linear combination of f of r and f of r plus ei. It was a linear combination of both of these guys. It was a linear combination of both these locations. And then the whole, so given any r, for every r there is such a linear combination. And so I was able to get a distribution of such pairs. And the distribution is over a random choice R. So because of this, it's a short linear combination. Short, it's a 2 linear combination, or in which this marginal over here is uniform, marginal over here is uniform. So we will try to do the same thing to construct the code over here. So this will go via this notion called matching vectors. M will be some, so the matching vector M will be some positive integer. N will also be some positive integer. So, and we will be working in general in the ring Zm. By this I mean integers mod mz. We'll be working in several objects. One of the objects we'll work is this ring. Zm. M is not mass. M is in fact it's going to be crucially not prime. Later on, right at this point, for the first how long? For the first 20 minutes, M can be arbitrary based on this one. Later on, we'll see I'll know how to do the construction only when M is not a prime. So, matching vector definition. So L is some subset of Zm minus some subset of non-zero points in this ring Zm. We'll say that two vectors u and v. So u will be u1, u2, all the way up to uk. V is going to be also v1, v2, vk. And it's both of them are k-length vectors, but each ui and vi themselves are vectors. They are going to be elements in Zmn. Each of them are going to be n-length vectors, and it's k n-length vectors. You can think of this as a matrix if you want to. The matrix structure won't help us. It's just that there are k vectors. I have k vectors u, k vectors V, but the vectors are mapped. That's the first vector here, this is the first vector here, this is the second vector here. So, and there's a match. So the reason it's called matching vectors is there is a, I'll say that UV is a L matching vector. If the following, if for all I in K, if you look at UI dot VI, that's the usual inner product, UI dot VI, so that's right by linear form itself. Actually, let me not write it this way, let me write it this way. UI dot. So these are two vectors, I'm taking their dot product, but the dot product, notice, is happening in the ring Zn, because they are both n-length vectors in Zn. This should be equal to 0. So whenever two matched vectors are taken, their dot product is taken, their thing should be 0. And for all I not equal to j in K, UI dot Vj should belong to L. Is it clear what the definition of matching vectors is? It's a set of two. So I'm working with the ring Zn. I'm looking at vectors of length n, and I'm asking for k vectors, two sets of k vectors, but they're ordered. So that they're matching vectors. So they have k vectors and they have a corresponding matching k vectors. So that every pair of matched vectors, if you look at their dot product, that should be 0. And for all other pairs, the thing should lie in the small set L. And what property of this we will use? We will use the following. So, of course, can I construct such objects? So we'll use this theorem of Prahladh. We'll prove this theorem also later in the class, but for now we'll assume it. Prahladh's theorem from 2000. It says that if M is a composite number, this is where the composite name M with T distinct prime factors. For example, M could be 6 and then P will be 2 because it has 2 and 3. Then there exists an explicit construction of matching vectors. UV L matching vectors UV such that the following conditions are satisfied. For every n. So I can, you tell me n. So m is fixed. M is one fixed number. So you're working with a small ring. So think of m as 6 or something for now. You can think of m 6. For every n, I can give you arbitrarily long vectors with size of L, we would call L, will be at most 2 power t minus 1. That's the number of possible non-zero elements that you will find out. That is, it won't take all possible values in M, but only 2 power t. So notice once I say it's non-zero, it could be any of the remaining M minus 1 guys in the ring. But I'm claiming it's not any one of the M minus 1, right? It lies in the small set L. And the size of the set is L is only 2 power t minus 1. Notice 2 power t minus 1 is significantly smaller than M because M has P distinct prime factors. In particular, N is larger than the product of the first P prime factors, which is larger than 2 power t. So m is strictly larger than 2 power t. And I'm telling you, I'm getting a number which is much, m is considerably larger, and I'm going to give you a thing which is much smaller. Whenever if things are non-matched, this thing falls in a small set here. And one, I'll just finish one more. And I can get a large set of such vectors. The whole point is I want to get, and I can get k, which is exponential in log n to the power t by log n to the power t. Okay. What's your question?
So, for example, for n equals to 1,
N equals 1, it's trivial. It's a no, n equals 1 is a trivial. Equals 1. N equals 1. Basically, then I want to get just an element in the.
you just say, or if it want to be a single number, a single number.
No. How can you take L to be? Because you want matched guys to have the dot product to be 0.
The 0, 1 means.
Huh?
In already is.
So if n is 1, ui dot vi is just multiplication in the ring. Therefore, you have to take not necessarily, it's a composite ring. So you have options over there. Yeah. It's composite. M is composite. This one will let you do. It will let you get the point will be we want to get more and more such kits. In fact, as in composites, we can do this. Yeah. So because it's composite, you can do this. You can get guys which are non-zero, but set that their dot product is 0. Because you're working in the ring. So these are with respect to these are all happening. This is in ZM. These are both are in ZM. These operations are happening in ZM. So what is we'll come to Prahladh's construction towards the end of the lecture. But Prahladh's construction says you give me any m, which is basically you rule out the fact that it's not a prime field, it's some composite. You think going modulo there is some composite number. Then for every possible n, I can get a large number of matching vectors, k to be exponential in this quantity, such that the non-matched guys are all going to a very small set. They're all going to match to only 2 power t minus 1 location. This is Prahladh's construction. Okay, we'll come to this later, but what we will see is I give you this construction. From this construction, we will construct so Efremenko's main observation, the main theorem is the following. So what we will do is the following. We will now work with a field FQ. Finite field. Let gamma be in FQ star. That be some element in the multiplicative one, and such that the order of gamma be equal to m. Thus, m will be the m which we are talking about. And so, therefore, notice that m has to be a factor of q minus 1. Because you know that gamma of q minus 1 will become 1. So, m has to be a factor. So, now let's think of taking a field fq and a number m, which is a factor of q minus 1. And that's going to be our starting point. That's going to be a starting point. What does Efremenko say? Efremenko says the following. FQ is a field. And m is a factor of q minus 1. Suppose UV is a L matching pair of L matching vectors in Z and N, where E And notice that necessarily L is 0 is not contained in L. And of size K. Then we'll define a code. Then there exists the L plus 1, 1 by 3 L plus 1 LDC. We'll construct a code from this matching vector.
Are these vector size in is it in power in
What?
is it in power?
The number of vectors are
Oh.
number of vectors are K was the Zn power n is not when I mean size, I mean the number of that was the number represented U1, U2, U3. And furthermore, this code will be it will be a code based on the matching vectors. It will CUV. The code will not require, it will require only V. It will be from FQ to the K to FQ to the N, where N is Q minus 1 to the power N. That the code will be this. Notice
the K in the code is the same as
the K in the code is the same as the K over there. That's important. K in the code is same over there. And the length of the code is going to be Q minus 1 to the power N. This is basically there because I'm going to come up with some polynomial with K coefficients. And I'm going to evaluate the polynomial on FQ star to the N. That's why FQ star to the N and FQ star is Q minus 1. I'm going to evaluate. That's going to be the reason why this is the case. But let's see that Grodman's construction told you K was slightly, it's a little more, it's more than N. And the target capital N is exponential. If K was like poly N, then this would have been an exponential growth from K to N. Because K is now super polynomial because of the way we have constructed it, the blow up is a sub-exponential growth. The blow up is a sub-exponential growth. So that I won't be doing. So all I want to say is since N is exponential. So let's think of, so the way we are going to think of this is Q is constant, Q is going to be some constant size field, M is going to be some constant. That's the setting we are going to be thinking of. So you can in fact think of, you can fully for this class and think of M to be 6. This is prime composite number 6. Q is something such that I want M to divide Q. So I want 6 to divide Q minus 1. Yeah, take one of that. So take the prime field of size 31. So think of Q and M as constants for now. Therefore, this N is exponential. So capital N is exponential. K is super polynomial by Grossman's construction. Hence, rate is sub-exponential. You can explicitly write it down, but it will be a sub-exponential. That's why you get sub-exponential, and this is what actually surprised people that they exist a code with sub-exponential rate, which can be as, and in fact, it will be just L plus 1. And L plus 1 will be for us, it will be what was L? If M is 6, L is 3. Therefore, it will be actually just a 4 query locally decodable code. The code which we will construct will be 4 query locally decodable. Okay. So let's do the code construction. So what we will do is, so I'm given some, look at the message. Even before the message. So this is going to be like a read Muller code, except that it's going to be a multivariate. So basically it's going to be the evaluation of a multivariate polynomial. That's what's going to happen. That's what's going to be the code. You're going to view the message as the coefficients. So you're going to view the message as coefficients. Some multivariate polynomial. And the code word as evaluation of polynomial on all points, not in entire FQM, but in FQ star n. That's why you have capital N is Q minus 1 to the power n. So this is how we're going to do. Now I tell you what is this one. It's not going to be like read Muller. Read Muller, we talked about polynomials which you have all monomials less than a particular degree. Here we have only certain monomials. The allowed monomials are basically you're going to have one monomial for each I in K. So it's going to be a linear combination of K monomials. That's why the message space is that you can view the polynomial as a, once you give me K field symbols that represents the polynomial. And what are these monomials? These are going to be the monomials. So for
What is the product xi into xi?
which one?
I don't know.
I haven't yet described it. I'm going to describe the monomial. This is a particular monomial. I of x1, x2, xn is a monomial. And I'm going to describe what the monomial, which is the monomials I'm going to look at. So what is the monomial I'm going to look at? It's xj, j going from 1 to n. But I'm going to come, if the monomial is going to come with a particular power. What's the power it's going to come up with? I'll take V of I. It's the ith monomial. So I'll take V of I. V of I, notice, is an n symbol vector. I'll just take I'll use that vector as the exponent vector. That is the monomial obtained by using Vi as the exponent vector. Okay. So these are the allowed monomials. I give you V1, V2, Vk. Each one is representing a monomial, and those are the only monomials in this one. So now I give you any method, if I give you any message, A1, A2, Ak in FQ to the K, we map it to the polynomial PA of x bar, which is just summation of AI chi I of x bar. Okay. So that's this one, and the code word and the CV is basically CV is the evaluation of PA on FQ star. That's the description of the code. Okay. Fair enough. So the description notice will require the other, it only requires the V vector. We will use the fact that the V vectors have matching vector U to be able to decode. So that's the description of the code. So the decoding. So use U vectors to decode. In particular, to decode coefficient of chi I. To decode the coefficient of chi I. So you're given the evaluation now. I have to basically, given the evaluation of polynomial, I need to decode the polynomial back from it. In particular, I want the message is basically I decode what's the coefficient of chi 1, chi 2, chi m. Decode coefficient, we will use. Obviously, we are going to use the corresponding matching vector. UI. The UI will be used to recover. Fair enough. So that's going to be a strategy. One small notation before I can describe this process. First notation I'm going to use is suppose X and Y are two things in FQ star N. We'll define X Hadamard product Y. This basically is the another vector FQ star N such that its element wise this one is just Xi times Y. So it's I have two vectors, I take the Hadamard product means coordinate wise I'm taking the product. And then several other things are just going to be for ease of notation. Suppose I have an F in FQ star N and a H in ZM. Then when I mean X to the power H, I basically mean take every coordinate and raise it respectively to the power H. X to the power H is basically X1 to the power H, X2 to the power H. It's just shorthand for this. This one. And I'm going to do the other way also. Suppose I have an A in FQ star and a U in ZMN. So I have, think of this as an exponent vector, and I have an A. When I mean A to the U, what I mean is first take A to the U1, A to the U2. Sorry, please way I'm going to write this. A to the U1, A to the U2, A to the U. Okay. So it's not usually very defined, but I'm going to use this sort of shorthand notation to keep things. Now, notice the matching vectors are giving something which happen in the exponent. Matching vectors UIs and VIs are happening in the exponent. So I would like to ask, so given L is the possible answers of the matching vector, possible possible bilinear forms matching vectors. So a construct B, which is basically gamma. The gamma, recall, was an element of order M in it. It's going to be basically gamma to the L, where L is in L union 0. So these are so notice all the elements in B are distinct elements. Firstly, it has the element 1. Let me not call it 1. Let me not say. So let me not put 0. I define B to be this. Notice that size of B is exactly size of F because you haven't yet hit the order, and furthermore, 1 is not in because L does not have the element. Since 0 does not belong to them.
Why is the second? Why is the second statement?
Which second statement?
Only not be equals to it.
Because there is no this one. I have assumed that this is because the order of gamma is M.
Okay, and we use it.
Yeah. So because the order of gamma is in M, there won't be any repeats over here. Yeah. So this is the case. So because of this, I want to claim we have the following simple claim. There exists non-zero elements C0, C1 all the way up to CL. So let's call L to be the size of L. CL in FQ such that the following two conditions are put. 1, summation Ci, I going from 0 to L is 0. 2, CH beta to the power H, I going from 0 to the L is H is H and H and I are the same. I don't know why I do H over there. I want to say, sorry, this is not what I want to say. This I want to say. This is equal to 1. This is equal to 0. That is, there exists some set of this one, so that if I take elements in beta, so basically these are think of these as coefficients of a polynomial. It says there exists a polynomial which on all of B it vanishes, but when you plug in 1 into that polynomial, it gives you the value 1.
For all beta and B.
Yeah, for all beta. And the proof is just take polynomial, which is product of x minus beta by 1 minus beta in. You take that polynomial. Certainly, for whenever I plug in a beta in B, it vanishes. When I plug in 1, it is 1. And this polynomial has exactly L plus 1 coefficient. That's I'm not using. So this is going to be the linear combination I'm going to be using. Okay. Yeah, 1 is not in. So I'm using all of this element. So what happened in Reed-Muller? Reed-Muller, he wanted to record a particular point. He passed a line through that point. And evaluated the point. We are almost going to do the same thing. We won't pass a line through the point, not a usual line. We will pass what is called a multiplicative line. It will be clear what I mean. Not a formal this one. It's not a one, but this is an object which we will talk about now. So what's a multiplicative line? We have just like a regular line, there will be a point that we'll care about. A regular line, how would you specify it? You specify it by a point and a direction. So x plus py are the various. So I give you x is the point on the line, y is the direction. The points on the line are specified by x plus py as t ranges over the field. Here also we have the same thing. X will be in some FQ star. This is a point. Y will be also an element in FQ star n. That's the direction. That's the direction. And in fact, the direction which we will be looking at will all be of the form, y will all be of the form gamma to the power some ui. Those will be the, it will just take gamma and look at this vector, and that's going to be the direction we're going to look at. And I'm going to define the line L of xy, the multiplicative line, as x dot y to the t in is the line clear? So these are the lines I'm going to be looking at. And ideally, so you can take any point in any direction as long as they're in FQ star m. Notice that all the points in this line are still in FQ star m. And the direction we'll be looking at will be only direction of the form y, gamma to the power ui. Do one small claim. Once we see that claim, the decoder will be clear. We have all the ingredients with us. What I want to say is for all ij in K, these are the number of matching vectors. Let x be any element in FQ star m and h be any element in Zm. So let's look at the evaluation of the jth monomial at the point x dot product with gamma h ui. So it's the point x, the Hadamard product with gamma raised to h ui. Is this the definition? Everything it makes sense. One thing that you notice, x is the way we're going to eventually choose gammas will be fixed, the direction will be fixed. Unlike previously, the direction was the random thing which we chose. Here you choose the point to be the random, the point to be random. Notice as I range over random points x, this one ranges uniformly over FQ star m. That is, I basically take any direction and I multiply it, Hadamard multiplied with a random point x. It's just going to move to a random point in this one. So we will be using the uniformity of this over the space FQ star m when x is random. But let's look at what is this. Let's see the proof. Let's look at the proof. Let's just evaluate this. So what is pi j x dot gamma h ui? So what is this? This by definition, pi j is just pi. Should I use some other notation? I should use for the not about pi xl. L going from 1 to k, and sorry, not xl, so it is xl, and here I had to take gamma h ui. I have to take the lth symbol in it and multiply it with vi, the lth symbol. Let's look at this again. So what is pi j? It's going to take the individual guys over here and raise them to the power pjl. That's how we defined it. Because that's the exponent with. But what comes in the base is going to be xl, but it's going to be dot producted with the lth component of this. The lth component of this is gamma to the power h ui, the lth component of it. So what is this? This is just, let's take out the XL part of it. XL part of it is just ij of x. That just take the excess part of it. The other one, what do you notice? It's just gamma into h, the dot product between ui and vj. That's what is going to happen when I multiply it out. Now, what do we know? This guy, if I equals j, this is 0. If I not equal to j, this is an element of L. And an element of n is going to give it. So I want to claim this is equal to gamma jx if I equals j. Otherwise, it's gamma jx into some beta ij to the power h, where beta ij belongs to p. Because that's, I know it's a gamma for x. So that's all I want to claim. I want to claim it's of the form gamma for jx if I equals j, and it's gamma jx into beta ijh, where if I not equal to j for some beta ij, no, but then we are done. Notice it that so chi j when evaluated at this point is either chi jx or this guy. So now if I take the appropriate CH linear combination, so I will read off, if I take the CH linear combination of the polynomial of these guys, when I take the appropriate CH linear combination, this will just cancel out if I not equal to j, and only this will survive. So I want to, because the CH combination, notice it will, CH combination had this feature. If you plug in elements from B, things from B, it would vanish. Otherwise, it would not vanish. Therefore, I want to say this basically gives you the following: the decoder. It suggests the following decoder. So you're given the input y going from FQ star n to FQ with the promise that there exists a k in FQ to the k such that delta of y and CV of a say is less than whatever capital N by 3l plus 1. That's that you're given this as an oracle input. Also, you're given an I in k. It's an explicit input. So what's the algorithm? The algorithm is going to be now pick random x in FQ star n. The first step, query y on x dot y x dot gamma ui x dot gamma 2 ui all the way up to x dot gamma l ui. These L plus 1 points. Notice each one of them is random. Gamma is this one, therefore multiplying by x is random. And what will you have to do? You just output I'm going to take a particular linear combination of these guys. What is the linear combination I'm going to take? I'm going to take h is 0 to L, CH, y of x dot gamma h u l. So I'll take this linear combination. Now with good enough probability, this L plus 1, these random L plus 1, and none of them are therefore, you would actually get the right value polynomial of these. But the right value, notice it, that polynomial is the linear combination of the monomials. Now, if you do the check, the only monomial that will survive is the monomial corresponding to I. So basically, I have to do this. I And I will finally do chi. Do this and then I. So I'll just shave that off. Okay. If you look at this one, if y at x dot gamma hui is equal to PA x dot gamma hui for h being equal 0 to L. This happens with probability. Happens with probability. How much? It happens with probability exactly L times L plus 1 times epsilon, which is for us. It's exactly 1 by 3 because I have chosen this to be the error to be 1 by 3 L plus 1. If L plus L, so with error at most, which happens with probability 1 minus this, so that's greater than, that's equal to 1 minus 3/3, that's equal to 2/3. Now when it's this, you just use the previous two things. You will realize in this case, but summation h equals 0 to L PA x dot gamma h ui into ch, this whole gamma I. So let's forget about gamma I for now. What is this quantity? I want to say this is summation h equals 0 to L ch. PA itself can be expanded out as j going from 1 to k, gamma j x dot gamma hui. Now, because of this previous claim, in this summation, the only thing that will survive is the I, all the other guys. So you'd only pick up at the end of this, this will only end up in gamma I of x. So you pick the right guy out, everything else will get vanished, and then anyhow, therefore that's the analysis of the whole thing. Okay. Question on this. It's a very clever, it uses the fact that there is this matching vector to build these lines, short lines. The lines are just L plus 1 long, the number of points period on the line. So that, but it's a distribution over lines, so that every point on the line, the marginal distribution of every point on the line is the uniform distribution. I might write one, just write this without. So for all I in K, probability that the decoder, probability of randomness of the decoder when given I, given Y I, outputs AI is greater than or equal to 2/3. That's the conclusion of all of this system. I'm not, you follow this. Okay. Yeah, so now the question now comes to why do such matching vectors exist? Let's go back to Prahlad's construction. Want to ask? Why does such an object exist? We use such an object to actually construct this one. So let's now want to ask, do question is, do matching vectors, existence of matching vectors I'll take 10 minutes and I'll finish this. It's going to be a nice complexity result. Why such matching vectors is used. So the construction of locally decodable given matching vectors here. It builds the set of polynomials. It's not the remolar set. It's a different set based on different monomials, but it happens because the coefficients of these monomials, you can extract them. Give me any for any monomial, there exists a set of multiplicative lines, a random set of multiplicative lines, such that, and these lines are not the number of query points in each line is only L plus 1. But if you query the point, if all the points on a particular line are correct, you can get this particular coefficient. That's what is happening out here. And the existence of such codes depended on the fact that they were matching vectors of this. So now what we want to ask is why do they exist such matching vectors? Grolmus has constructed this. We will now here are going to give Sudan's construction of matching vectors. Using something called the OR representation. So what's an OR representation? So I want to come up with a polynomial that's going. So what's the OR function? So let's take the standard OR function. And we'll look at the OR function on R bits. It's the obvious function if x1, x2, xr is sent to 0 if x bar is 0 and 1 otherwise. The standard OR function. I want to represent this as a polynomial. So what I want is I will say a particular polynomial P in Zn. M is the same M as we started off with, and you will notice here is where the fact that M is composite is going to play a big role. So I'm going to look at M. It's an R variate polynomial. Represents or if the following is true, that is, if x bar is the all zero vector. So notice the polynomial is over the ring. The polynomial principle can take coefficients from the ring, but I'm going to evaluate the polynomial only on 0, 1 vectors. So if x bar is 0, then I must have P of x bar to be 0. If x bar is not 0, then I must have P of x bar to be not 0. That's all I want. I don't care what value it takes in this model. You take any element in the ring. So this is what we mean by OR representation. So this is what we mean by OR representation. And you will see if you I don't know if you get a done complexity or so in the complexity course there might sometimes people will. So in the latter part of the course, there will be Rasborough and Smolensky's results that are talked about. And there they will ask about what is the smallest degree of polynomial P that satisfies this property. Notice there is obviously a polynomial of degree R. You can construct a polynomial of degree R that satisfies this. Because just write down the R polynomial or function as a polynomial, it will have degree R. So the question is, what is the smallest degree of any polynomial P that represents R in the following sense. And results of Rasborough and Smolensky show that the degree is at least omega r if m is prime. Basically, if you're working with a field. This is what Rasberg's model scheme. But what happens if m is composite? Can the degree considerably reduce? And this is where what Barrington and Rudis showed. Suppose m is composite with t distinct prime factors. Then there exists an OR representation over Zn with degree order r to the power 1 over t. So the more the number of prime factors, distinct prime factors, the degree will keep dropping for the representation. And furthermore, what they show, one thing which you can see in there, this one. Furthermore, if you look at this representation, if you look at the set of all p of x bar, when x bar is not equal, x bar belongs to 0, 1 to the r minus the all zeros. You know, this is going to be set of all this one. This set is at most of size 2 power t minus 1. That is the set of all possibilities it can take is 2 power t minus 1. Okay. 3 more minutes and I'm not going to do Beagle, Barrington, Rudis. So I'll post notes. So I have tech notes for the entire lecture. Along with these notes, I'll post that also, where the Beagle, Barrington, Rudis will be described for m equals 6. In which case, I'll give you an example of a square root r polynomial which matches this. This is where we show that once you go to non-composites, you can have the things that represent things with considerably lower degree than what happens over the primes. But I want to claim that once you are given this, a matching vector is almost trivial. So why is a matching vector trivial? So I'm going to give construction. We'll just do this in 3 minutes and we'll wrap up. Construction of matching vectors using BBR construction. BBR or representation. So what does BBR tell you? BBR tells you there exists this polynomial P. So BBR gives you BBR uses P. Uses P in Zm x1 to xr such that P of the P of x is 0 if x is the all zeros vector and it belongs to some set L if x belongs to 0, 1 to the r minus the all zeros vector where 0 does not belong to L and size of L is less than 2 power t minus 1. This is what BBR. This is just rewriting BBR. Now I want to say from BBR, we can construct for each y in 0, 1 to the R, I can construct a polynomial Py of x, which is just the OR polynomial but shifted. In the sense it is going to be equal to 0 if x is equal to y and belongs to L if x 0, 1 minus x. I claim you can
minus one.
minus y. And you just this is just translate the thing to translate the origin from x to the y, and you get the same. Is this clear that you can do this? That is basically what you should do is if yi is equal, so what this called one minus x. That's basically this. So essentially that's basically what it is. I'm not going to write it down. The Pyx is just the OR polynomial, but now shifted from the location of y rather than the all zeros. But now I want to claim the OR polynomial. This is basically the matching vector. Look at Pyx. Pyx can be written as Py alpha of times alpha of x. I'm just writing it as a monomial basis. And I know that the degree of Py is small because that's where x was given to be a small degree. What do I know? I know that in the monomial basis, what is the monomial basis? The monomial basis is exactly the basis of R less than or equal to D, where D is some order rth root of 1 over T. That's the monomial basis. Now I claim you do have exactly whatever we want. That is the matching. I will call alpha x as the ui's. So I will construct u and v as follows. Construct uv as follows, where k is exactly 2 power r. And so u is basically going to be an ux for each x in 0, 1 to the r. V is going to be vx for each x in 0, 1 to the r. U of x is just going to be defined to be alpha of x. V of x is going to be, let's call it V of y. V of y is P alpha y. That exactly tells you that is when these are the same vector, when I choose the same vector, the dot product is 0. When they are different vectors, it falls in a small set here. That's exactly what matching vectors were meant to do. And that's the matching vector construction. By the way, so this has been asked if all representations have even smaller degrees. We don't know how to do it. So there are several open questions over here. If over composites, the all representations have even smaller degrees than, for example, over Z6. I want to give a representation for R. Question is, what's the degree? This one will tell you the exists degree square root R. Question is, do they exist smaller? We don't have an answer for this. We don't have an answer. So we don't have an answer, best answer for the OR polynomial. We don't have a best answer for the matching vectors and for the LDCs. All that we know is something better than non-trivial can be done. We believe things can be done, improved considerably, but it's open at this point of time. So the OR construction is also very simple. The BBR construction, it just uses some Chinese remainder theorem and stuff. So I will post lecture notes. I have lecture notes from when I taught this course previously, when I did this. So it's LaTeX lecture notes. I'll post that in the web page, which will have even the proof of this for the special case when M is 6. Okay, let me short this one. Let's start this.